Welcome, friends. On this episode of 2 minus 3 equals negative fun, we are factoring trinomials. All right, we have seen a few examples like this in class, and we've practiced a couple of them, but it doesn't hurt to go back and revisit a few examples and practice them. All right, so we are asked to factor this polynomial, x squared minus 15x plus 54. All right, so we're looking for factors of 54. So two numbers, when they multiply together, they make 54. And when they add, and I know it's add because of this sign, so their sum has to be negative 15. So to factor this apart, we're going to have an x term as our first for each set of parentheses here. And I'm going to go ahead and put the signs in. And I know that the two signs in here are both negative. And if you wanted to revisit another video from a prior lesson, you should know how we know what signs go in here. But this tells us that these two signs are the same. And this symbol tells us what the signs are. Now I'm going to erase a bunch of this to get some stuff out of our way. And again, that should serve just as a little bit of a review. All right, but we need factors of 54 that add to make 15. So the factors of 54, we have 1 and 54, 2 and 27. 1 plus 54 is not 15 or negative 15. 2 plus 27 is not negative 15. 3 goes into 54 18 times. 3 plus 18 is not 15. So now I'm going to keep going with my factors. 4 does not go into 54. I got ahead of myself. I shouldn't have written that. That's all right. 5 does not go into 54. 6 does. 6 times 9 is 54. And 6 plus 9 is 15. So when you multiply those, you get 54. If you add 6 plus 9, you do in fact get 15. But we've got to get a negative 15. So I'm going to plug my numbers in here. We have 9 and 6. We already know the signs are the same. They're both negative. And if you FOILed that back out, you would get x squared minus 15x plus 54. Welcome, friends, to an exciting episode of 2 minus 3 equals negative fun. We are factoring trinomials with a leading coefficient greater than 1. Stay tuned. All right, we've seen factoring trinomials that are of the form x squared plus bx plus c. And now we're going to look at examples where this value is bigger than 1. And I do this a little bit of an unorthodox method. So it's different than what's in the textbook. It's different than what some sources will show you. So tune in, make sure you take good notes. If I can take this, my strategy is to transform this where we have a coefficient in front that is equal to 1. And if we can do that, it becomes a more familiar problem. So the first thing I'm going to do is take this value and move it to the end. And when we do that, we're going to multiply here. All right, so we now have the polynomial x squared minus 7x minus 8. Now I'm going to factor it the same way that we've done previous examples where we're looking for factors of 8 that add, in this case, actually subtract to get us 7. So I'm going to list the factors of 8, 1 and 8, and we can go ahead and stop here, guys, because 8 minus 1 gets you 7, and we need a negative 7, so we're going to end up doing 1 minus 8. So setting up my parentheses here, and just like the rules we used in previous examples, this sign tells us that these two symbols are going to be different. So we're going to have a plus and a minus in here. And then this symbol tells us the larger value. So my larger number between 1 and 8 has to go here. All right, but we're not done. You cannot stop here. Since we moved this 4, now I've got to take the 4 back through, and we're just going to divide by 4. So we're really going to undo that original step. And by doing this, it's the same problem. In here, we're going to simplify our fractions anywhere we can simplify. So 8 over 4 simplifies to just 2 over 1. And now x plus 1/4, that doesn't simplify. So I'm going to take the 4 and just sneak it in front of this x value. And now we have factored 4x squared minus 7x plus 2. And you can write it like this, or you could write it with the larger value in front. They really mean the same thing. For now, we'll take either one. It's probably better practice to put the larger value in front, but for now, we'll take it either way. And if you FOILed this back out to check your answer, you get back to our original, so it works. All right, we're asked to factor 12x squared minus 3x minus 9. And the first thing that we're going to do, and the first thing we should always do, and I probably should have pointed this out in previous videos, but our first move is to check for a GCF. So we want to see, is there a greatest common factor between 12, 3, and 9? And there is. In this example, our GCF is 3. So the first thing I'm going to do is factor out a GCF. And when you do that, you're really dividing. So all of this gets divided by 3. And you're left with 4x squared minus x minus 3. Whatever the GCF is, that's going to stay outside in front of the parentheses. And now inside these parentheses, we're going to factor the polynomial 4x squared minus x minus 3. And just like in the previous example we saw where we could move the leading coefficient to the end to set up a familiar example, or a familiar problem type, we're going to do that same process here. So I'm going to take this 4, move it to the end. And now we're looking for factors of 12. So factors of 12 that subtract to make 1. The reason I know it's 1 is there's an understood 1 in front of this x. So it's factors of 12 that subtract, and I know it's subtract because of this sign, that get us negative 1, or 1 really. And down here I'm going to set up my parentheses for us. We're going to have different signs in here. The larger is going to be negative. I'm going to go ahead and put my symbols in here. Factors of 12, we have 1 and 12. Those do not subtract to get us -1, so we know it's not those. 2 and 6, those don't subtract to get -1, so it can't be those. 3 and 4, well, those look tantalizing because 3 minus 4 is negative fun, or -1. The larger value here is 4, so it goes in this spot. Now up here, since we moved this 4, we have to move it back through and divide. But only these terms get divided. This doesn't get divided by 3 because it was never affected by our little move here. Simplify your fractions where you can. 4 over 4 just simplifies to 1. 3 over 4, we're not going to go into decimal expressions or anything like that, so we just sneak this 4 back in front. And we end up with 3 times x minus 1 times 4x plus 3. Welcome, friends. On this episode, we are factoring by grouping. All right, here we see a polynomial that's got 4 terms, which is a new one for us. And we're going to learn to factor this by grouping. But before we do that, let me explain a little bit of what you can expect to see here. So if you'll go back to our examples where we were foiling, and we would have something like x plus 5, and I'm just making up an example, and then we would have like x minus 3. And we would FOIL this doing first terms, and then outer terms, and then inner last, right? Well, really what you're doing is the distributive property, and you're multiplying x times x minus 3, and then you're multiplying plus 5, that's this part, times x minus 3. And you'll probably notice right away that you see this x minus 3 written twice, but in the original problem it's only written once. And I show you this because in just a second we're going to see this exact same thing present itself, but in our final answer we just write it one time. So we'll refer back to this in just a second. For now, let's get back to the example of x cubed plus x squared plus 2x plus 2. Well, the first thing I'm going to do is group terms together. So I'm grouping x cubed plus x squared, and I'm grouping 2x plus 2. So now in this first set here where we have x cubed plus x squared, I'm going to factor out a GCF. Now the GCF is only what's in common in this group. So for this group, the GCF is x squared. So when you factor out x squared, x cubed divided by x squared is just x, and then x squared divided by x squared is just 1. And then in this set over here, we have a GCF of 2. All right, so I'm factoring out a 2 from this set. And when you divide this by 2, and you divide here by 2, you're left with x plus 1. And now something should jump out at you here, and you probably already noticed it without even me having to say it. But now we have an x plus 1 and an x plus 1. We have 2 of the same thing. And over here just a second ago, I told you we're going to end up getting 2 of the same thing. And this is really just evidence of the distributive property. You should get the same thing in here. If you don't, you've probably made a mistake somewhere. So now I'm going to take this value and this value, our two GCFs. We're writing those in a set of parentheses together. And now what was left when we took out a GCF will go in the second set. And if we FOIL this back out to check our answer, doing first, outer, inner, last, we would get x cubed plus x squared plus 2x plus 2. So it works. All right, we're going to factor by grouping here. And we have 4 terms in this polynomial: x cubed minus 9x squared plus x minus 9. So I'm going to start by grouping these, and I'm going to group the first 2 terms. And then I'm going to group the second 2 terms. And when you do that, you get so now we have x cubed minus x squared in one set of parentheses here. So in this set, I'm going to factor out a GCF. And the GCF in this one is x squared Now, just as a reminder or a little bit of a refresher, factoring out is really just dividing. So I'm dividing all of this stuff in here by the GCF of x squared. And when we do that, we're left with, or take what your GCF is and put it out front. And here we have x minus 9. Now I'm going to do the same thing in this second set over here. And you might notice, well, there really isn't a GCF, because you have x minus 9. So really what we're going to do is factor out a GCF of 1. So if you're looking at it and there's not a greatest common factor, you're probably going to factor out a 1. Because if you're factoring by grouping, you're going to have something to come out, because you got to get your 2 sets of parentheses. So I'm taking out a 1. Essentially, that doesn't change anything inside here. We're still left with an x minus 9. And again, just to remind you, you can check to see if you've done it correct, because you should get the same thing in each set of these parentheses. And we do. So now I'm just going to rewrite this with your 2 like greatest common factor terms. Those will form one of your binomials or one of your sets of parentheses. And then what you're left with, or whatever you had duplicates of, those will be your second binomial, but you only write them once. And if you were to FOIL this back out, you could check your work to see, does it get us back to the original? And you would get x cubed minus 9x squared plus x minus 9. So it works. Welcome, my friends, on this episode of 2 minus 3 equals negative fun. We are factoring special case trinomials. All right. The first special case that we're going to look at is a difference of perfect squares. Difference meaning subtract, perfect squares meaning perfect squares. And there's a pattern that sets up and falls into place for each of these. And the problems will typically look like you'll have two numbers squared, or perhaps they won't have the exponent of 2, but they will be perfect squares. And they're going to be subtracted from one another. That's the difference of perfect squares part. And these will always factor into this setup here. So that's a common pattern that we're going to see. And to show you why, just real quick, if you were to FOIL this back out, so you did first terms, outer terms, and then inner, and then last, you would end up with a squared minus ab plus ab minus b squared. And when you combine like terms, you see that these cancel, and you're just left with a squared minus b squared, a difference of perfect squares. So let's take a peek here at an example. To factor the polynomial, it is a difference of perfect squares. Looking at this, x squared is a perfect square because if you took the square root of x squared, well, you just get x. And if we take the square root of 25, not the square root of negative 25, but the square root of 25, you get 5. So these are both perfect squares. So to factor this, you take the square root of your first term, take the square root of the second term, which we've already determined is 5, and the signs have to be different. So that's factoring a difference of perfect squares. All right, for this example, we are asked to factor a difference of perfect squares. First thing we look for is a GCF. There's not a GCF between 81 and 4. 81 is a perfect square. 81x squared actually is what we're looking at here. It is a perfect square. So if we took the square root of 81x squared, we get 9x. If we take the square root of 4, we get 2. So these are perfect squares. It's a difference of perfect squares. So to factor this, it follows a nice little pattern that's pretty easy for us here. So you take the square root of the first term, square root of the last term, and we get different signs. So we have factored the difference of perfect squares. All right, this example looks a little different than what we've seen. It says negative 3x squared plus 48y squared. First thing I'm going to do is factor out a GCF. And our GCF for this is going to be negative 3. So really I'm dividing each of these by negative 3. (48) divided by negative 3 is negative 16y squared. So in the original problem where we had negative 3x squared plus 48y squared, we didn't have a difference of perfect squares. However, when we take out the GCF, we do now have a result of perfect squares. All right, so to factor this, I'm going to take the square root of x squared, which is just x, and then the square root of 16y squared. So you ignore that negative or minus sign, and that's just 4y. Keep your greatest common factor that we took out in front. The square root of the first term, square root your second term, and we get a plus and a minus. And now we have factored a difference of perfect squares. Hello friends, for this episode of Mr. Johnson's math class, we are factoring special case trinomials. Alright, before we jump into the examples here, a perfect square trinomial is going to follow a pattern, and they all are going to set up following really a similar setup of a squared plus 2ab plus b squared, or you might even see a squared minus 2ab plus b squared. Now, it won't always be a squared and b squared. Those might just be perfect square numbers. And when we see some examples, it'll make a little bit more sense. But these will always factor out to a final result of a plus b squared or a minus b squared. And let's look at an example here that'll help make a little bit more sense. So x squared minus 4x plus 4. You may notice this term is a perfect square, because if we take the square root of x squared, you just get x. And this term is also a perfect square, because the square root of 4 is 2. So this is a special case perfect square trinomial. So if we factored this the traditional way, so let's say that you didn't know that this was a special case and you just started factoring this like normal. Well, you look for factors of 4 that add to make 4. Well, your factors of 4 are 1 and 4, 2 and 2. Well, 2 plus 2 is 4, so you would factor it apart. The signs are the same and they're both negative. All right, well, here's what you need to notice. You have the exact same thing in both of these parentheses. Well, if you end up with the same thing, to put it in simplest form or factor completely, since we have the same thing twice, it's multiplied by itself twice, so you end up with x minus 2 squared. If you notice that you've got a squared term, and this middle term happens to be the sum of your middle terms doubled. That's what in the pattern here where we showed the 2ab, that's what that means. But if you happen to notice this, you could just do the little shortcut where you square root the first term, square root last term. This is the symbol that goes in the middle here. And then you write your final answer squared. So you can do it the long way, and it's really not that long. You're just skipping one step. Or you could look for a shortcut. We are asked to factor the polynomial perfect square trinomial of x squared minus 10x plus 25. You may notice, and it might jump out at you, that this is a perfect square and this is a perfect square. If you didn't and you just wanted to factor it normal, so x squared minus 10x plus 25. Factors of 25 that add to make 10. Well, our factors of 25 are 1 and 25, and then 5 times 5. So it can't be 1 and 25, it's got to be 5 and 5. This tells us the signs in here are going to be the same. This tells us that they're both subtraction signs. Since you have the same thing in both of them, to put it in simplest form, you have x minus 5 squared. All right, in this example, we have 49x squared plus 14x plus 1. And in previous examples, when this leading coefficient isn't 1, we did the thing where we would move this term to the end, and we would do all that extra work. However, what should stand out to you is this is a perfect square. And the square root of that is just 7x. 1 is a perfect square because the square root of it is 1. So if we factored this apart, you take the square root of the first term, square root of the last term, and whatever symbol is here. This tells us that we would get the same symbol if we had two sets of parentheses. This tells us what symbol it gets. So whatever symbol that is, that goes in here. But it's the whole thing squared. And now we have factored the special case of 49x squared plus 14x plus 1.